Hello everyone, I am Dr. Fawzul Atik. I am giving some series of lecture for the course Discrete Mathematics. So today we'll start a new unit called the Elementary Number Theory. And we will see that, okay, whatever things we know from since our childhood, we'll be recalling them, and with that we'll learn few more things, right? So without wasting time, I'll start what is the divisibility. So if a and b are integers with a not equal to 0, and then we say that a divides b if there is an integer c such that b is equal to ac. Basically, a divides b means what? That b by a is equal to some integer. So that we will say that a divides b, right? And therefore, you can say that b is equal to a times c. Right. So you will say that a divides b if there is an integer c such that b is equal to a into c, or equivalently b by a is an integer. Yes, that's what. When we say that a divides b, we say that a is a factor or divisor of b. Yes, a is a factor or divisor of b, and b is multiple of a. And how you write it as a notation? So you will use that notation a divides b. Right, we called it as a divides. Like, I'll give an example. Like, I have 3 and we know that 3 divides 12. Why? Because 12 is equal to 3 times 4. So therefore 3 divides 12. Right, this is the notation we'll use. Now I'll give you an example that, okay, which does not divide. Like 5, does it divides 27? No, right? So 5 does not divide, so we'll write it as 5 does not divides 27. So this is the notation. And we can express a divides b using quantifiers as there exists c such that ac is equal to b. This is just a notation. Clear? So we'll say that some integer a divides b if you have b is equal to a into some another integer. This is the thing. So we have few more examples. 3 divides 12, but 4 does not divide 7. 5 divides 0 because 0 is divisible by any integer. So 5 divides 0. So we can have that 5 divides 0. So these are the thing we know already. These are very easy. Only thing we are learning the notation. Now I have a very interesting problem, and if you just put a little bit of your mind, you can able to answer this question. Let n and d are positive integers. How many positive integers not exceeding n are divisible by d? How many positive integers not exceeding n are divisible by d? Right? So here what are the things are given? N and d, two positive integers are given. So I'll take some example first. Maybe your n is, suppose your n is equal to 40, correct? And your d is equal to maybe 5. Then try to look this question. How many positive integer not exceeding 40 is divisible by 5? Now what are all such positive integer which are not exceeding n but divisible by 5? So all the integers divisible by 5 are what? 5, 10, 15, 20, 25, 30, and 35, then 40. These are the integers. Now how many such things are which is not exceeding 40? How many such things are there? 1, 2, 3, 4, 5, 6, 7, 8. So here 8 number of positive integers we have. Correct? So now if I take n is equal to maybe 42 and d is equal to 5 itself, then what are the integers not divisible by n, is divisible by 5 but not exceeding 40, 42? It thus answers are same: 5, 10, then 15, 20, 35, and 40. In this case also answer is 40, up to 40, and the answer is 8. So what basically we are doing, that 40 by 5 is what? 40 by 5 is 8. What is 42 by 5? It is 8 point something, right? 8.8.4. So 8 point something. But both the cases answer is 8. Therefore, can you guess what should be the answer? Yes, the answer will be, it is the floor function, right? Floor function of n by d, because this n by d may not be always integer. but you have to get how many positive integers are there not exceeding n but divisible by d. So in general, how do you represent this? So you have to say that all the integers which are divisible by d are of the form what? D, 2d, 3d, right, dot 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 up to m into times d. But your condition is your the largest among them should not be exceeding n. So therefore, what is your job? Your job is to find the maximum number m such that m into d is less than n, right? So your m should be equal to n by d. But m is an integer, so n by d may not be an integer. So what is the largest m? So you have to take n by d, floor function of it, right? So I'll show you the answer. So this is the answer. Positive integers divisible by d are the multiples of d which are d, 2d, 3d up to md, where m is the largest integer such that md is less or equal to n. And therefore, m must be equal to n by d, floor function of n by d. Right? So the answer is n by d, floor of it. I hope it is clear. Okay, next. We have few results related to this division. Let a, b and c are integers where a not equal to 0, then if a divides b and a divides c, then a divides b plus c. We all know, right, that if a 3 divides 7, 3 divides maybe 15, 3 divides 6, so 3 divides their 15 plus 6, 21, right? We all know. So a divides b, a divides c, a divides their sum. Yes, it is clear. We know. So we can prove this very easily. How to do? Now we have the part 1, how to prove the first part. A divides b and a divides c. A divides c means what? Which will imply that b must be written as in terms of a into c. Right? A divides b. So b is divisible by a. So b should be written in the form of a into some. I will not write c, but I will write it as a into m. m1 or something. Because c is already involved here. So I write a into m. Right? Again, I have a divides c. What it will imply? It will imply c must be written as a into some another integer, a into n. You have to prove that a divides b plus c. How to prove that? Just from these two, add these two values. So b plus c is equal to m times, sorry, a times m plus n, m plus n times a. What does it mean? That b plus c is a multiple of a because m plus n is an integer. Therefore, a must be divides b plus c. Proof is done. So the first part is done. Very easily you have to. What about the next one? I have a divides b. Then a divides b into c for any integer. Yes, we know 3 divides 15. Then 3 definitely divides 15 into some any integer. 15 into 2, 30. Right? Very easily you can say. So I have a divides b. I have a divides b. What can you say from this? So I can easily write b is equal to a into n. Now what is your job? You have to prove that a divides b into c. Okay, so what you will do? You multiply both sides by c. So you can write b into c is equal to a into c into n. Now b into c you have written in the form of a times c into n. Right? So a it's a multiple of a. Therefore you can immediately declare that a must be divides b into c. Right? So easy, very easy. What about the third one? How to prove the third part? The third one says if a divides b and b divides c, then a divides c. This is basically, it is saying that like a divides b, that means 3 divides maybe 9, and you have 9 divides 27, and definitely you can say that 3 divides 27. This is what it says. But how do you prove this? You can very easily prove that a divides b. What does it mean? B can be written as a product of a into n. So a into n. Now you have b divides c. You have b divides c. What can you say from that? C can be written as b into another integer m. Now put this b value from the first one. So therefore c is equal to a times n into m. Therefore what you got? C is equal to a into some integer n into m. So c is a multiple of a. Therefore a must divide c. Therefore a must divide c. This proof is also done, right? So these are the very small proof, but these are interesting and these are useful as well. So this is the proof that whatever we have discussed, it is written here. Now I have one more result, which is a corollary of this previous theorem. What it says, if a, b, c are integer with a not equal to 0, such that a divides b and a divides c, then a must divides mb plus nc, where m and n are integer, which you can easily prove that from the previous theorem. How? You have a divides b. Can't you say that a divides m into b? How? From the part 2 of the previous theorem. If a divides b, then a divides b into c for any integer c. Similarly, I have a divides b, therefore a divides m into b for the integer m. Similarly, I have a divides c. From this, I can say that a divides n into c from the same part 2 of the previous result. And now I have a divides mb, I have a divides nc, I have, therefore I definitely have a divides their sum from the part 1 of the previous theorem. So therefore I can say that a divides mb plus nc, right? So therefore this is the corollary of the previous theorem. Very easily you can prove it by taking the help of the previous theorem. So this is the final one. So first we apply part 2 and then we apply the part 1 of the previous theorem and we have proved it, right? So these are few result we had related to this. Next we will discuss something, we will discuss about something that we have learned again since our childhood. We know it, but we learn this in a, like, this is little formal way, the division algorithm. Let a be an integer and d be a positive integer. A is any integer and d is positive integer. A can be negative integers, A can be positive integers, A can be 0, but d should be positive integer. Then there are unique integers q and r with 0 less or equal to less than d, such that A is equal to dq plus r. Now these things you learn from your childhood, right? Like I'll give you something. Maybe you are saying that 22 you have. Then you are dividing this by 5. How do you do? So your quotient is 4, then it is 20, and you got a remainder as 2. Then can't you write that, okay, therefore you can write 22 is equal to 5 into 4 plus 2, correct? So this is the similar kind of thing. So this is the dividend, this is the divisor, this is the quotient, this is the remainder. Dividend, divisor, quotient, remainder. Right, and therefore you can write the dividend is equal to divisor into quotient plus remainder. Now here what is our restriction? The division algorithm, there is a restriction that a can be any integer but d is a positive integer. That part if you have such thing, then we'll have unique integer q and r with 0 less or equal to r less than d. Therefore r is a non-negative quantity and r is less than the divisor. R is a non-negative quantity and r is less than the divisor. A is equal to dq plus r. And other thing is, in the inequality given in the division algorithm, d is called the divisor. Yes, d is the divisor, like this. A is called the dividend, this is the a, this is the dividend. Q is called the quotient, this is the quotient, and r is called the remainder. All of us know it. Here is a new notation we have learned, that quotient and remainder you can write it as quotient is equal to a div v, a div d, and remainder is equal to a mod d, a mod d. Right? So in the previous, in this example, what is the quotient? 4. You can write it as 22 div 5. And what is the remainder? 2. You can write it as 22 mod 5. That means if you divide 22 by 5, you will get quotient as 4. If you divide 22 by 5, you will get 2 as a remainder. Clear? So what is the thing you have? You have your a can be any integer, d is a positive integer. This is very, very important one. Then you will have unique quotient and unique remainder such that the remainder is always non-negative and less than d. Please be careful, remainder is always positive quantity and less than d, because d is also a positive integer. Then you can write a is equal to dq plus r. Clear? I'll give some example. You find out what is the quotient and remainder. So what is the quotient and remainder when 101 is divided by 11? So what you will do, 101 is divided by 11. So our childhood method way I'm doing only. So what you say, 9 11s are 99, and therefore you get 2 as a reminder, right? So quotient means that it is 101 div 11. What is this value? The quotient is 9, therefore it is 9. And what is the remainder? Remainder is 101 mod 11. This value is 2. And you can write it as 101 is equal to 11 into 9 plus 2. See, the remainder 2 is less than 11 and remainder 2 is greater equal to 0. So we have 0 less or equal to 2, which is less than 11. Yes, everything is satisfied. So therefore the quotient is 2 and the quotient is 9 and the remainder is 2. Right? If you have understood, can you do this problem? What are the quotient and remainder when minus 11 is divisible by 3? When minus 11 is divisible by 3. So this kind of problem, please try to understand. Minus 11 is the dividend and divisor is 3. It is positive. But we said already, a can be any integer. So a can be negative, a can be positive. So minus 11, it is a valid problem. Now you should get the remainder as positive and less than 3, right? So you have to represent minus 11 in such a way that you should get remainder is positive quantity and remainder is less than 3. How to do that? So you will say minus 11 is equal to, you will see minus 11 is equal to 3 times. Now several students do the mistake as 3 times into minus 3 then minus 2. It is matching, but then what you will say, quotient is minus 3 and remainder is minus 2. But I said remainder is less than greater equal to 0. Remainder is non-negative. Right? So this is not a valid expression. This is not a valid expression. What you should write, you adjust such a way the quotient, you do it such a way so that you will get the remainder as positive. What you will do, you will say minus 11 is equal to 3 times you do minus 4. So what is the value? Minus 12. But you have to get minus 11. So you will say minus 12 plus 1. So you get it is minus 11. So therefore, this is dividend is equal to divisor into quotient plus remainder, where remainder is also satisfying the greater equal to 0 quantity and less than 3, right? Because 1 which is greater equal to 0 and less than 3. So everything is satisfying. So therefore, the quotient is equal to minus 4 and the remainder is equal to 1. Problem is done. And why the remainder is positive, we will see that it has a lot of implications if you express it in this way. I hope this is clear. Okay. Now we have a like another new terminology called modular arithmetic. So what we'll learn from there, that we'll say that congruent modulo thing we'll learn. What we'll say, if a and b are integers and m is a positive integer, then a is congruent to b modulo n. A and b are any integers and m is a positive integer. Then we say that a is congruent to b modulo n if m divides a minus b. Right? And then we will use the notation a is congruent to b modulo n. This is the notation. So basically we have, suppose I have that 12 minus 2 whose value is 10 and it is divisible by 5, right? So 12 minus 2 is divisible by 5 because 5 divides 12 minus 10. So I can write therefore that 12 is congruent to 2 mod 5. 12 is congruent to 2 mod 5 because 12 minus 2 is divisible by 5. Clear? I can give many other example. Maybe 17 is congruent to 3 mod 7. Can't I do? Yes, because 17 minus 3 is 14, which is divisible by 7. So therefore, you can write that. Let me give you another example. maybe 22 is congruent to 4 mod 5. Is it true? 22 minus 4, 18. Is it divisible by 5? No, in this case it is not. Therefore, 22 is not congruent to 4 mod 5. Correct? So this is the notation of not congruent. This is the notation of not congruent. Clear? So if something is not congruent to, like A is not congruent to B mod M, then we can write that A is not congruent to B mod M. This is the notation. Clear? We have several other examples. 17 is congruent to 5 mod 6. Yes. 24 is congruent to 12. 24 is congruent to 14 mod 6. It is not, right? So 24 is not congruent to 14 mod 6. This one, minus 7 is congruent to 5 mod 6. Will it be minus 7 minus 5 minus 12? Yes, it is divisible. So 6 divides this. Therefore, 7 minus 7 is congruent to 5 mod 6. Right? So these are some examples that you confirm that, okay, this way you can write that something is congruent to something. Now we have one result related to this congruent modulo M, and it says that let A and B are integers, and let A and B are integers, and we have M is a positive integers. A and B are any integers, and M is a positive integer. Then I have A congruent to B mod M if and only if A mod M is equal to B mod M. Right, I'll give you the previous example. Maybe 17 is congruent to 2 mod 5. Correct? Now, according to this theorem, 17 congruent to 2 mod 5. Therefore, I will have that 17 mod 5. What is this value? What is this value 17 mod 5? It means that if you divide 17 by 5, what is the remainder? The remainder is 2. Another one, that B means 2 here, 2 mod 5. What is the remainder in this case? So 2 is, if you divide 5 by 2, what is the remainder? And remainder should be non-negative. Therefore, in this case also remainder is 2. Why? Because 2 is the dividend and 5 will do, we'll say it is 0. Quotient is 0 and therefore you'll get remainder is 0. So 2 is equal to 5 times 0 plus 2. So therefore 2 is the remainder. So in this case also remainder is 2. And that is what this theorem says. A is congruent to B mod M if and only the remainder of A divides M, like whenever you are dividing A by M, and it does remainder whenever you are dividing B by M are same. Right? So it has a very easy proof also, like you can see the proof. I am not discussing much. I am not writing the proof, but you can easily prove it. That if R1 is A mod M and R2 is B mod M, right? Then A congruent to B mod M means that M divides A minus B. This is given. Now you have to prove that R1 is equal to R2. How will say? Now R1 means it is the remainder when you divide A by M. So A must be written in the form of M into some quotient plus the remainder. So that quotient is Q1, you assume. Similarly, because R2 is equal to B mod M, so B can be written as that M into some quotient Q2 plus R2. So you can write in this way. And therefore, A minus B, from this expression, you can take this value. Now M divides A minus B, it is given, and M divides this part also. M divides this part. M divides A minus B, given. M divides this part because it is a multiple of M. So therefore M divides their subtraction. So basically what you get, M divides this part as well. But this part is what? For both the cases, R1 and R2 are less than M. So modulus of R1 minus R2 must be less than M. But it is possible when? Whenever R1 is equal to R2. Therefore, R1 minus R2 must be 0. Right? So this proof is not that important, but it is easy. You can easily see that and you can prove it. And the other way one, like if A mod M and A mod M and B mod M are equal, then you can easily say that A congruent to B mod M. Suppose R1 is equal to R2. Therefore, what you can say that A minus B must be Q1 minus Q2 because this part will be 0, R1 minus R2. And you can easily see that A minus B is a multiple of M, therefore M must divides A minus B. Done? Right? So similarly, we have another result which says that m be a positive integer, then the integer a and b are congruent modulo m if and only if there is an integer k such that a is equal to b plus km. A is equal to b plus km. So if a is congruent to b mod m, then we can easily say that if and only a is equal to b plus km. K is another integer. This is if and only. But this is again very easy proof. So if A congruent to B mod M, therefore M must divide A minus B. So A minus B can be written in the form of K into some M into some another integer K. Therefore A is equal to B plus K. And the other way, if A is equal to B plus K, you can easily say that A minus B is a multiple of M, and therefore M must divide A minus B. The proof is done. Therefore M divides A minus B means A congruent to B mod M. Right? So these are small proof that is, but the statements are very important. Like we have to use this statement in many places. We have another result. Let m be a positive integer, and if a congruent to b mod m and c congruent to d mod m, then a plus c must be congruent to b plus d mod m, and ac congruent to bd mod m. These proofs are easy. What you will say that if a congruent to b mod m, what does it mean? That a minus b must be written in the form of m into some integer, maybe k1, and I have c congruent to d mod m. Therefore, c minus d must be, you can write it as m into some integer k2, right? So just you divide it. So just add both the equation. So in both the equation, if I add, so a plus c minus b minus d must be equal to m times k1 plus k2. What does it mean? That a plus c, so I can write it as a plus c minus b plus d. You can write it as a multiple of m, because k1 plus k2 is an integer. Therefore, you can say that a plus c is congruent to b plus d modulo m. Modulo m. Easy proof. Similarly, how do you prove that that AC congruent to BD mod n? So like these two equation, you just multiply them. So you will write that AC minus uh, AC minus BC minus AD plus BD is equal to m times m square into k1 k2. We can write this part. Right? Now what to do? You have to prove that AC is congruent to BD mod m. So we multiply it both sides by this. Now what we can do, basically we can say that, okay, just a minute. Now what we'll do, not in this way, I will just do it from the previous, this equation. Okay, I have a is equal to, can't I write that from this I can write a is equal to the part 2 I am doing. Part 2 I am doing. This is the part 1. Part 2 is a is equal to, I can write a is equal to b plus m into k1. Right? And part 2, what we can write, and the other part, what we can do, we'll say that c is equal to d plus mk2. Right? Now let us multiply. So we will say that a into c is equal to, what you can say, it is bd plus mdk1 plus bmk2 plus m square k1 into k2. I can write that, and therefore I can easily take it common. So this is bd plus, take m as common, dk1 plus bk2 plus m into k1 k2. And therefore you can see that AC minus BD is a multiple of M. AC minus BD. Therefore you can say that AC is congruent to BD modulo M. This proof is also done. right? So these are the small group. If you just do a little bit effort, you can easily prove them. Similarly, we have a few more results. Like if n is a positive integer and m be any integer, then a congruent to b mod n imply that m a congruent to m b mod n. So you can multiply any integer. This will also not create any problem, right? So you can multiply any integer in the both side, so that you will say that it is still modulo n, still divides by n. And now if n is a positive integer and a congruent to b mod n, then a power k is congruent to b power k mod n for any non-negative integer k. So you can take the power of it also, right? So a power, it take the power of a and then take the same power of b. This will be still congruent modulo n, right? So these are the something I thought to discuss for this lecture. All the content I have taken from this book only, right? So I hope these are useful. I hope you feel these are easy. So do practice some problem like this, and in the next video we'll continue the same thing. Thank you very much. We'll come up with a new video in the next lecture.